The next problem we want to take a look at is counting words where we have limits on consecutive repetitions. What does that mean? Well, we're going to ask the question, how many words of length n are there, just from the alphabet A, B, a two-letter alphabet, where we cannot have two A's in a row. So we can have any number of B's in a row, you just can never have two A's in a row. Anytime you have an A, it has to be followed by a B. If we had no conditions and wanted to count the number of n-letter words, of course the answer would be 2 to the n. But here, because we have this weird condition, we're going to choose some new notation. We'll call it W sub n, and we'll let that denote the number of words satisfying this condition of length n. Now, let's look at a quick example. What is W1? Well, I claim it's just 2. I won't even write them down. You have the word A and you have the word B. What is W2? Well, what are all the possible two-letter words? You have BA, you have BB, you have AB, and we're not going to allow AA because that has two A's in a row. So you're only going to have 3 possibilities. How would we get W4? Well, let's try to count them. If I start with an A, then the next letter has to be a B. And that means if I'm looking for W3. I don't know why I had written a 4. We want to find the number of 3-letter words. If I start with an A, the next letter has to be a B, and then it could be followed by an A or a B. So if I start with an A, these are the only possibilities. Well, if I start with a B, I can put anything next. I could have a BA or a BB. But if I have a BA, the next letter has to be a B. If I start with a BB, I could have a B or an A. So you can see very simply there are 5 words possible here. And you already see from just the way I tried to organize and count W3, the number of 3-letter words, the total was 5, it's helpful to split them into the cases where the word starts with an A or where the word starts with a B. So I'm going to have new notation. A sub n will denote the number of words of length n starting with A. And of course, I mean words that satisfy the condition. Bn similarly will denote the number of words of length n starting with B. And then immediately we're going to see we can start to build a recurrence relation by noting that W sub n is just A sub n plus B sub n, because every word either starts with an A or starts with a B. Here W3 was 2 plus 3. There are 2 that start with an A and 3 that start with a B. But notice that if a word starts with an A, the next letter has to be a B. So how many words are there of length 3 that start with an A? It's the same as the number of words of length 2 that start with a B. And in general, we can say that A sub n is just B sub n minus 1, because every word that starts with an A of whatever length, say length n, a B follows, and we could just count words of length n minus 1 that start with a B, and we'll get the same thing. So A sub n is just the same as B sub n minus 1. But what about words that start with a B? If I start with a B, like these, here's the initial B, the next letter can be either an A or B. If I'm counting words of length 3 that start with a B, I can have all possible words of length 2 here. I could have A's or B's to begin with, and literally every possible word of length 2 can go there. So similarly, I can say that B sub n is just the same as Wn minus 1. If I have a B as the first letter, I could just ignore the first letter and have a word of one letter shorter, and the number of those is W sub n minus 1. Well, we can put those together, since A sub n is B sub n minus 1, and B sub n is Wn minus 1. B sub n minus 1 is just the same as Wn minus 2. And then W sub n, I'll rewrite it here, which is A sub n plus B sub n, is just the B sub n, which is Wn minus 1, plus the A sub n, which is Wn minus 2. And we can certainly use that for all n greater than or equal to 3. Now this recurrence relation should be familiar. It's exactly the same recurrence relation that we saw with the Fibonacci sequence. Notice that for this sequence, however, we're starting with W1 is 2 and W2 is 3. Whereas for the Fibonacci ones, we had F1 was 1. Remember, F0 was 1, but we're ignoring the n equals 0 case here. F2 was 2. So the Fibonacci sequence starts with 1 and 2 and has Fn is Fn minus 1 plus Fn minus 2. This is for n at least 3. I say at least 3. If we put in F naught, you could start that at 2. But either way, it's the same recurrence relation, just different starting values. Does that mean we could solve for W sub n? The answer is yes. In fact, we've already done it, since you can recognize the W's as just the same as the Fibonacci numbers, but starting in a different place. Because here, remember, we had F3 is 3, so you'll notice W1 is the same as F2, W2 is the same as F3, and because they follow the same recurrence relation, they'll all continue like that forever. In other words, what we see here is that W sub n is exactly the same as Fn minus 1. This is true for all n. Let me write this correctly. We can look at all sorts of different variants, and some of these are looked at in the book. How many words are there? The variant we're going to look at now is how many words are there of length n from the set A, B, with the condition that we cannot have 2 A's in a row, just as before. But now we'll add another condition that we can't have more than 3 B's in a row. So if we put both of these conditions on, how many words can we have? And we want to do a process similar to what we did the last time, but we want to use a more organized way of keeping track of how many words we have. So just as before, we will let Wn be the total number of words, and these are all meeting the conditions, 2 conditions that we have. I won't rewrite that. Wn is the number of words of length n. And just like before, A sub n is the words that begin with A. Well, these are words of length n. And B sub n is words that begin with B. And I want to draw a tree diagram the way they do in the book, because it's a useful thing in helping us see what's going on. For the tree diagram, I'm going to imagine we start a word, and we can start with either an A or a B. And the word will be n letters. So we'll have the letters moving to the right. This will be, of course, the first letter here. If we start with an A, we can't have 2 A's in a row, so we just have to have a B in the second letter. If we start with a B, we could have an A as the second letter, or we could have a B as the second letter. So this is the second letter. If we have a B here, we could go on with an A or a B. If we have an A here, it has to be a B. And if we have a B here, remember we started with a B, then another B, we would still have an A or a B. And then we can just continue that for the fourth letter. We have an A here, so the next letter has to be a B. We have a B here, we have B, B. We can still have another B, or we can have an A. From this B, we could have an A or a B. From this A, we have to have a B. And from this B, we've had 3 B's in a row. We can't have any more. There has to be an A. Now, this helps us count things very easily because we can see W1 is 2. We just count if we want one-letter words, we have either the A or the B. W2 is 3. We either have AB or BA or BB. The number of things in this column tells us W for that number N. In this case, W2 is 3. W3 is going to be 5 because we can go ABA, ABB, BAB, BBA, or BBB. Just the 5 things in this column represent the 5 words. Now this looks pretty similar to before, but now you note for column 4, we have only 7 things. It's very much like the previous problem, only instead of adding the 5 and the 3, we have 1 less. The reason we have 1 less is because the second condition kicked in, and we can't have more than 3 B's in a row. And then we continue like this without putting the A's and B's. I'll just show you. Think of the upper one as an A and the lower one as a B, or here it's just a B. Then we can't have another B, so we only have an A now after this because we have 3 B's in a row. From this A, we have to have a B. From this B, we could have either an A or a B. From this B, we could have either an A or a B. And from this A, we have to have a B. And you can just count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in position 5. So W5 would be 10. Is there a way to get a recurrence relation for the sequence W sub n? We know it begins like this, but what would the recurrence relation look like? Well, just like before, we'll start writing down things we know. Words of length n either start with an A or start with a B, so W sub n is A sub n plus B sub n. But what can you say about A sub n? Again, just like before, if a word starts with an A, then it has to continue with a B. So the number of words that start with an A is the same as the number of words of one fewer letter that start with a B. So you get B sub n minus 1. But what can you say about B sub n? If we start with the B, we could either be a shorter word by 1 that starts with an A, that there would be A sub n minus 1 of those, or we could go down here. But I don't want to write it in here. Here I can't just say B sub n minus 1 because now I've got 2 B's in a row and that would lead to this condition sooner. So I've counted all of these with A sub n minus 1, but here I'm going to have to say either I have an A, in which case I have all the words that go on from this point, and that's just A sub n minus 2. They're now shorter by 2 letters and they start with an A, or I'm down here. Well, if I'm down here, I've got 3 B's in a row. And how many words start with those 3 B's? Well, the next letter has to be an A, so I can just write A sub n minus 3 here. So now I've got some interesting equations. W sub n is A sub n plus B sub n. A sub n is B sub n minus 1, and B sub n is A n minus 1 plus A n minus 2 plus A n minus 3. One thing interesting to notice, if I just put in this equation for B sub n in the top, I get W sub n is exactly A sub n plus A n minus 1 plus A n minus 2 plus A n minus 3. Now here's where we're going to be able to get a recurrence. The goal is to get a recurrence for just the sequence W sub n. In other words, eliminate the A's and B's. And how are we going to do that? Well, we can write W sub n in a different way as an plus bn. Instead of an plus bn, I'm going to replace the an by bn minus 1, and we'll get bn plus bn minus 1. Now what I'd like to do to get the recurrence just in terms of the w's is get rid of all the a's and b's, and the easiest way to get rid of all the a's and b's is to match an a sub n with the b sub n to get w sub n. A sub n minus 1 plus b sub n minus 1 is w sub n minus 1, but I have nothing to match a n minus 2 and a n minus 3. But actually I do, because w n minus 2 is just an minus 2 plus b. Well, actually, let me change that. I apologize. Using this equation above, wn minus 2, I can write as bn minus 2 plus bn minus 3. That's just from the previous equation, but substitute n minus 2 for n. And then, sorry, I kind of ran over there. If I add wn and wn minus 2, I get b sub n plus bn minus 1 plus bn minus 2 plus bn minus 3. So when I take wn and add to it both of these, plus wn minus 2, I get all of these a's and all of these b's. That's an plus an minus 1 plus an minus 2 plus an minus 3, plus I have a bn plus bn minus 1 plus bn minus 2 plus bn minus 3, which is exactly an plus bn. That's wn plus the next is wn minus 1 plus wn minus 2 plus wn minus 3. In other words, if you look at this first formula here, wn plus wn minus 2, that can be written just in terms of the w's. Then I just cancel a wn here. I cancel the wn minus 2 there, and we're left with wn on the left and wn minus 1 plus wn minus 3 on the right. This will be true for all n, which are at least 4. And if we combine this with the fact that we know w1 equals 2, w2 is 3, and w3 is 5, this recursion relation will define the sequence entirely. Notice that after w3, w4 would just be w3 plus w1, which is w4 is 7, that would be the 5 plus the 2. w5 is 10, that would be the 7 plus the 3. And we could go on and on and on. w6 would be the 10 plus the 5. You'd get 15. And it would keep going like that.